Hello students, welcome to Memoneet. I am Sakti Swaroop, teacher at Memoneet. I am MBBS student of one of the government medical colleges of Odisha. So I hope you all are absolutely fine. We will start today with a new chapter, that is error. First of the topic error, we will start with significant figures. So what are the rules to find out the significant figure here? So the first rule, that is all the non-zero digits are significant. Okay, let's say we have some value that is 563. Okay, so there are three significant figures. Okay, so in the, for example, here it is given that is 1984. So it has four significant figures. Then second rule, that is all the zeros between two non-zero digits are significant. Okay. So let's say we have here that is 10,806. Here we have 10 and here we have 10. So it have these zeros are also significant because these are present in between the non-zero digits. Okay, let's say we have 2005. Okay, so this is non-zero digit, this is non-zero digit, and these two zeros are significant because they are present in between the non-zero digits. So the number of significant figure here is 4 and here it is 5. Okay, then third rule, that is all the zeros to the left of the first non-zero digit are not significant. Okay, let's say here it is given that 00108. Okay, these two have no importance. Okay, it means they are not significant. So we have the significant figure here, that is 3. Rule, that is if the number is less than 1 and the zeros on the right of the decimal point but to the left of the first non-zero digit are not significant. What does it means? Let's say we have here that is 0.002308. Okay, here these two zeros are left of non-zero digits. Okay, but it is right to the decimal point. They are not significant. So we have significant figure here, that is 4. That is for the 2308. 4 significant figures, that is for the 2308. Okay, then the next rule, that is the trailing zeros to the right of the last non-zero digit. It is last non-zero digit in a number with a decimal point are significant. Okay, so what it is trying to tell, that is here we have the non-zero digit, that is 8. After that, okay, after that 0 is there which will be significant in case of when there is any decimal number. Okay, let's say we have 2.060. Okay, here we have the after the decimal point there is a non-zero digit, that is 6, and after that there is another 0. Okay, so this is significant. So we have the significant figure here, that is 4. The rule 6 says that the trailing zeros in a number without a decimal point are not significant. That is, let's say we have the number that is 15600. Okay, the trailing zeros after the non-zero digit, they are not significant. Okay, but in case of when there is any decimal point, like this case, okay, it have the decimal point here, after the non-zero digit any trailing zeros are significant, but here in the when we have no decimal point after the non-zero digit, the trailing zeros will not be significant. Okay, we will have three significant figures. For example, here see that is 01000. Okay, 0100100. Here the trailing zeros after the non-zero digit, and before the non-zero digit there is another 0. This is not significant and these two zeros are not significant. So we have the only three significant figures here. Only three significant figures. Okay. if the number comes from some actual measurement, then the trailing zeros become significant. For example, we have mass equals to 100 kg. We, after the non-zero digit, that is 1, here there is 2 zeros, but it is represented in some measurement. So we, in this case, the trailing zeros are significant. So we have 3 significant figures here. Okay, 3 significant figures. Rule 6 says that when the number is expressed in exponential form, the exponential term does not affect the significant figure. Okay, let's say we have some value here, that is 12.3. Okay, 12.3. We can also write 12.3 as 123 into 10 to the power minus 1. Okay, and also we can write 1.23 into 10 to the power. So in this case, here the minus 1, 10 to the power minus 1 and 10 to the 1 will not affect the significant figure. In each of the case, we have the significant figures here, that is of 3 significant figures. Here also 3 significant figures. Addition and subtraction. Let's say we have 12.587 minus of 12.5. Okay, so here after solving it, we get that is 0.087. Okay, so how we will represent this? The result of the result should be represented as the number of decimal places which is present in the which have lesser decimal places. Okay, let's say we have here the lesser decimal places, that is 12.5. so this have only 1 decimal places, so the answer will be, result will be represented after the decimal, that is only 1 number, so we can write that is 0.1 after rounding it out. So this will be our answer. I want to say that the number of decimal places in the result should be equal to the that term which have the lesser number of decimal places in the operation. Okay, multiplication, let's say we have 5 multiplication, let's say into 0.125. so if we calculate it, it comes to be 0.625. okay, so here we have, that is after the decimal places we have three decimal places. In this decimal number we have 3 decimal places, but here we have, that is 5 point, let's say we take it as 5.0. okay, here we have 2 decimal places, so the result should be find out that is having the 2 decimal places, that is sorry 2 significant numbers, that is 0.62. here it have 2 significant figures, so the answer should be obtained as the 2 significant figures. Okay, so this will be the answer for this. One question, that is length, breadth and thickness of the metal sheet, that is 4.234 meter and 1.005 meter and 2.01 centimeter respectively. Give the surface area and volume of the sheet to correct number of significant figures. So we can write the length is equals to 4.234 meter and breadth is equals to 1.005 meter and the thickness is equals to 2.01 centimeter. It means we can write 0.0201 meter. Okay, so here the significant here is 4, here is 4 significant figures, 4 significant figures, and here is 3 significant figures. Okay, so we know that the area of surface area of the cuboid, that is let's say S is equals to 2 whole into L into B plus B into B plus T into L. Okay, so if we put this all this and try to find out, the answer will come to be, that is 8.720978 meter square. Okay, but here basically what I want to tell you, that here we have the lesser number of significant figures, that is for the thickness, that is we have 3 significant figures, and the result should be equal to that of significant figure which have the lesser number of significant figures. So that is for the answer for the surface area will be 8.72 meter square. That's it, because it have the three significant figures which have the lesser significant figures of all these, that is for the thickness also. Okay, so if you try to find out the volume, volume is equals to length into breadth into thickness. If you want to try to find out the volume by putting all this, okay, we will find that is 0.0855289 meter cube. Okay, so this is the volume, but what will be the answer for the correct answer? Okay, so we must have the three significant figures only, that will be equal to that of that of the significant figure for the thickness, which are the lesser significant numbers. Okay, so our answer should be 0.0855, because after the decimal point and before the non-zero digit, this zero have no value, it is not significant. So our answer for this is 0.0855. I hope you understand this. Next topic, that is rounding up. To represent the result of an computation containing more than one uncertain digit, it is rounded off to appropriate number of significant figures. So let's try to find out how to round off. Okay, so the first rule says that if the digit to be rounded off is more than 5, then the preceding digit is increased by 1. Okay, so let's say we have 4.568 okay, so if you want to round up to three significant figures, so we can write 4.5, this have the 6 this digit is 6, which is greater than 5. Okay, so we can round it off up to the next number, that is we can write it 4.57. okay, the first one says like this. Let's say we have 6.87, so if we want to round up, okay, the 8 is greater than 5, so we can round it up to the next number, that is 6.9. so then second rule tells that if the digit to be rounded off is less than 5, then the preceding digit is unaffected and is left unchanged. Okay, so what it wants to tell, that is if we want to round it off like 3.94, so here we have the 4 which is lesser than 5, so if we want to round it off, we can directly write 3.9, because this can't be rounded because it is less than 5. Then the third one, that is if the digit to be rounded off is 5, then the preceding digit is increased by 1 if it is odd and is left unchanged if it is even. For example, okay, let's say we have 4.35 here, it is here the 5 is rounded off, because as it is the odd number, so we can round it to the next number, that is 14.4. but here let's say we have 5 and here it is even number, that is 4, so if we want to round it off, we can directly write to 14.4, because as it is even, so we will not change it. So now we will start with error. So difference between the true value and the measured value is of a quantity is known as error of the measurement. Okay, so if we classify error into different types, that is systemic or controllable errors. That is, systemic errors are the errors whose causes are known, that is they can either be positive or negative. Due to the known causes, these errors can be minimized. The systemic errors can be further classified into three categories. What is systemic error? That is, we know the causes for what the error is happening. Systemic errors, we have four types of error, that is instrumental error, environmental errors, and observational errors and random errors. Instrumental errors, let's say we have some problem in the instrument, that is any imperfect design, or we can use it in misuse type. Okay, so we have the instrumental errors here. So the next is, that is environmental errors. Environmental errors in any condition, that is if we have rise in temperature or loss in temperature, or in the case of increasing and decreasing of electromagnetic fields or dust, vibration, anything, this will be due to the environmental errors. And observation errors, we have the improper setting of the apparatus or the carelessness in taking observations. And then random error, so this said that the error is are due to the unknown causes. So we say, therefore we tell it as random errors, because the causes of these error are not known precisely. That is, they cannot be eliminated completely. Let's say the person repeats the observation for the n number of times. He can get any of the reading, different type of reading. So for this, if we want to decrease the error, so the number of observations should be made much more, so that the error will decrease. Okay, and we will get our precise value. The second type of error, that is gross error. Gross error arises due to the human carelessness and mistakes in the reading in the observers or calculating the and recording the measured results. So the errors can be minimized by increasing the sincerity and alertness of the observer. It all depends on the human, how we are taking the observations and how we are calculating it. Okay, then we will go for a representation of errors. Error can be expressed in following ways. That is, first is the absolute error. What do you mean by absolute error? The difference between the true value and the individual measured value of the quantity is the absolute error. So what do you mean by the true value? The true value that is given for the any setup. Okay, so we have the absolute error, that is del A. Okay, this is equals to the true value, that is, let's say we take it as small a. Del A is equals to the true value, that is AT minus of a measured value. Okay, the mean absolute error. Mean absolute error, it is the arithmetic mean of all the absolute errors and is defined as the final or mean of the absolute error, that is del AM or del A. Okay. Let's say we have the absolute error, it is found out, that is del AM. Okay, and we have the mean value, sorry, let's say it is del A, and we have the mean value to find out, that is del AM is equals to, we have number of observation, that is n, so del A upon n. We will have the number of observation, that is del A1 plus del A2 plus del A3 plus del AN up to del n. Okay, so upon whole divided by number of observation. So this is basically what we want to say, that is the sum of absolute error upon number of observations. Okay, so this is known as mean absolute error. Of relative or fractional error. What do you mean by this? This is the ratio of the mean absolute error upon the ratio of the true mean value. Okay, to the true value or the mean value. So let's say we have the absolute, here it is represented as the absolute mean absolute error, that is del AM. Okay, and the true value, that is mean value, that is AM. Okay, this is the relative or fractional error. Okay, that is what do you want to say, that is, it is mean absolute error upon the mean error, sorry, mean value. It is mean value. Okay, so this will be what? This will be our the relative or the fractional error. It is mean value. The percentage of error. Okay, so this is what? That is the mean, that is mean absolute error upon mean value into 100. Okay, So basically what do we want to say? It is the relative error into 100, or we can find it as percentage error. We can name it as percentage error. To figure out what we understand from those concepts, we have question here, that is, following observation we are taken in with a vernier calipers while measuring the length of the cylinder, that is 3.29 centimeter, 3.28 centimeter, and then carry on. Okay, so then find the most accurate length of the cylinder. Most accurate length matlab, so it means the mean value we have to find out. Mean value, that is equals to most accurate value, that is equals to 3.29 plus 3.28 plus 3.29 plus 3.31 plus 3.28 plus 3.27 plus 3.29 plus 3.30. Okay, there are number of observations, that is 1 2 3 4 5 6 7 8. Okay, that is 8 number of observations. So this will be divided upon 8. So the answer comes to be, that is 3.28875. So we can write up to 3 significant figures, that is 3.29 after rounding it up. So this will be the mean value or most accurate value. What will be the absolute error? So this is first for the first bit. Absolute error, we will, for the absolute error, that is del A is equals to the value given here, the observed value given here minus of the mean value. Okay, that is 3 point for the first step, it is 3.29 minus of 3.29. For the first, it is 3.29 minus of 3.29. Let's say we are trying to find out the first absolute error. Let's say it is A1. Okay, 3.29 minus of 3.29. Okay, this will be 0. Then for the A2, that is equals to for the absolute error, that is del A1, del A2. Okay, so del A2, that is 3.28 minus of 3.29 minus of 3.28. 0.29 minus of 3.28, that is equals to 0.01. What we are trying to do, that is mean value minus of the observed value. If we try to find out, that is del A3, that will be 0.0 centimeter. Okay, because 3.29. Then del A4, that is 3.31 minus 3.31 minus of 3.29. 3.29 minus of 3.31. Okay, this will be 0.02. As we are trying to find the absolute error, it will be always positive. Okay, and del A5 is equals to 3.29 minus of 3.28, that is 0.01. Del A6, that is 3.29 minus of 3.27, that is 0.02. Then del A7 is equals to 3.29 minus of 3.29, that is 0. And del A8, that is equals to 3.29 minus of 3.30, that is of minus 1. It will be 0.01. Okay, minus of 0.01, that will be 0.01. So these are the absolute error, mean absolute error. Mean absolute error, that is we have in the first case, that is del A. Let's say we have mean absolute error, that is del A. Okay, so we have in the first, that is 0.00 plus. In the second, that is we have 0.01. In the third, that is 0.00. In the fourth, 0.02 plus. In the fifth, that is we have 3.29 minus of 3.28, that is 0.01 plus 0.02 plus 0 plus 0.01. Okay, this will be divided upon 8. So the answer comes here to be 0.01 centimeter is the mean absolute error. Then the D, that is relative error. Relative error, what we are telling, that is del AM upon the mean value, that is a. Okay, so this will be equals to 0.01 upon the am, or the mean value comes here to be, that is 3.29. so if we try to find it out, it is equals to 0.003. Okay, and the last one, that is percentage error, that is this relative error into 100. It means 0.003 into 100, that is equals to 0.3% is our percentage error. We can write the length as the most accurate value, that is 3.29 plus minus of error, that is 0.330%. Okay, like this we have to represent the error of the expression of any observation we have taken. Here we will move to our next topic, that is propagation of errors in mathematical operations. The first rule states that the maximum absolute error in the sum or difference of the two quantities is equal to the sum of the absolute errors in the individual quantities. Okay, so let's we have some that is x is equals to a plus b. Okay, or x is equals to a minus of b. In both the cases, let's say we have the errors, that is del a and del b. So we can write x del x is equals to del a plus del b. So the final expression we will write, that is x is equals to a plus b plus minus of del a plus del b. Okay, this is how we will represent. Or when we also subtract it, so we will write x is x2. Let's say it is x2. x2 is equals to a minus of b plus minus of del a plus del b. So this is how we will represent our errors. And rule, that is the maximum fractional or the relative error in the product or division of quantities is equal to the sum of the fractional or relative errors in the individual quantities. We have x is equals to a into b, or we can have any, that is x is equals to a upon b. So here, if we find out, if we want to find out the error, that is del x upon x is equals to, that is plus minus of del a upon a plus del b upon b. This is how we will do in the multiplication and division type. The third rule, that is the maximum fractional error in a quantity raised to power here is n times the fractional error in the quantity itself. Okay, so this what we want to tell. We have x is equals to a to the power n. So in the error, it is represented as del x upon x is equals to n will be in coefficient. Okay, n into del a upon a. So this is how we will represent. Question: we have two resistors of resistance R1, that is 100 plus 3 plus minus of 3 ohm, and R2 is equals to 200 plus minus of 4 ohm. So are connected in series and parallel. Find the equivalent resistance of the series combination and parallel combination. So we know that in series combination we have, that is in series R equivalent is equals to R1 plus R2. Okay, so that is equals to 100 plus minus of 3, sorry, it is R1 plus minus of 3 plus 200 plus minus of 4. So if we want to solve it, that is 100 plus 200, that is mean value, that is 300 plus minus of, the errors are added, just added, that is 3 plus 4, that is equals to 300 plus minus of 7 ohm. It is like this. This is R equivalent. The parallel combination. Okay, let's say we have the formula, that is R equivalent is equals to R1 into R2 plus R1 plus R2. So let's find out for the mean value. Okay, that is we have the mean value, that is 100 into 200 upon 100 plus 200, that is 300. So this will be equals to 20,000 upon 300. So this will be equals to 200 upon 3, that is 66.66, 66.7 ohm. So this will be the mean value. So if we want to try to find out the error, we know that 1 upon R equivalent is equals to 1 upon R1 plus 1 upon R2. So if we try to differentiate it out, so dr dash upon R dash is equals to d R1 upon R1 plus d R2 upon R2. Okay, so in differentiating of 1 upon R, we have minus 1 upon R square. It is minus of 1 upon R square. This will have minus of 1 upon R square, minus of dr1 upon R1 square, minus of dr2 upon dr2 square. Okay, this minus will cut down. So we have, that is dr dash upon R dash square is equals to dr1 upon R1 square plus dr2 upon R2 square. Right? Delta R dash upon R dash square is equals to delta R1 upon R1 square plus delta R2 upon R2 square. Okay, so here we can also write delta R dash is equals to R dash square whole into delta R1 upon R1 square plus delta R2 upon R2 square. Okay, so in this, if we want to put the value here, delta R dash is equals to R dash square, that is 66.7 square whole into delta R1, that is 3 upon delta R1 square, it means 100 square plus delta R2, that is 4 upon 200 delta R2 square, R2 square means 200 square. So this will be equals to delta R dash is equals to 4, solve this out, this comes to be 16 upon 9. Okay, so the delta R dash, that is comes to be 1.8 ohm value, that is R equivalent is equals to 66.7 plus minus of 1.8 ohm. So this is our final answer. Another question, that is length and breadth of the rectangle are 5.7 plus minus of 0.1 cm and 3.4 plus minus of 0.2 cm. Calculate the area of the rectangle with error limits. Okay, so let's find out the mean value, or that is area, that is mean value of area, that is A is equals to L into B, that is 5.7 into 3.4. So this comes to be, that is 19.38 centimeter square. So let's find out the error, that is del A upon A is equals to plus minus of del L upon L plus del B upon B, length and breadth, L for length and B for breadth. Okay, so we have del A upon A is equals to plus minus of del L. So what is del L? 0.1 upon the length, that is 0.7 plus del B upon B, that is 0.2 upon 3.4. So if we solve this out, this comes to be plus minus of 1.48 upon 19.38. Okay, so this is this is what we find out, that is del A upon A. So if we want to find out the error, it is relative, and if you want to find out the error, that is del A is equals to plus minus of 1.48 upon 19.38 into A. What is A? A is 19.38. Okay, here we have find it out, the mean value, that is equals to plus minus of 1.48. Okay, so if you want to find the expression, that is the area is equals to mean value, that is 19.38 plus minus of 1.48 meters centimeters square. Okay, centimeter square. So this will be our final answer. We'll try to find out the least count. What is least count? The smallest value of a physical quantity which can be measured accurately with an instrument is called the least count of the measuring instrument. So this is an instrument, that is vernier scale instrument, vernier scale. So these have two values, that is one is main scale reading, main scale value, that is let's say its unit is m. Okay, and it have vernier scale, let's say, which have units is v. Okay, so we have the length of a main scale of vernier, sorry, of a main scale will be equal to length of the vernier scale. Okay, so we have, that is a into m is equals to b into v. So to find out the least count, that is least count is equals to main scale reading minus vernier scale reading. Okay, that is equals to m minus of v, that is we can represent v as v is equals to a m upon v. Okay, so this is equals to minus of a upon v whole into m. So this will be equals to minus of a upon b whole into m. Okay, question here, 1 centimeter on the main scale of vernier calipers is divided into 10 equal parts of 20 division of vernier scale coincide with 8 small division of main scale. What will be the least count of the calipers? It tells that there is 8 small divisions of main scale, that is 8 into m, we can write is equals to 20 division of the vernier scale, as it is coinciding. It is 20 into v. So we can write, that is vernier scale is equals to 8 upon 20. Sorry, it is 8 upon 20 main scale division. Okay, or we can write it is as VSR. It is VSR and MSR. Vernier scale division VSD and MSD. Okay, so vernier scale division is equals to 8 upon 20 main scale division. So this will be equals to if you find the least count, that is 1 MSD minus 1 VSD, that is equals to 1 MSD is let's say we are taking MSD, it as MSD minus of 1 VSD, it means 8 upon 20 MSD, 8 upon 20 MSD. Okay, so this will be equals to that is 12 upon 20 MSD, it means 3 upon 5 MSD. Okay, count will be 0.6 MSD, and for the MSD we have, that is MSD, 1 MSD is equals to 1 upon 10 centimeter equals to 0.1 centimeter. So we have 0.6 into 0.1 centimeter, that is equals to 0.06 centimeter. This is the least count. Here this is a screw gauge and we have the pitch here. Sorry, the least count is calculated as pitch upon total number of division in circular scale. Okay, pitch is given as, that is total number of it is the distance moved. Okay, it is the distance moved by screw on the linear scale upon number of full rotations given. Okay, so let's use this formula and let's solve one question. We have the spherometer has 100 equal divisions marked along the periphery of its disc. One full rotation of the disc advances on the main scale by 0.01 centimeter. Find out the least count. So here we have the piece that is equals to the total distance moved in one single rotation, that is 0.01 centimeter. Okay, so this is the pitch. So what will be the least count? That is pitch upon total number of division in the circular scale. Okay, so this will be is equals to 0.01 upon 100, that is equals to 1 into 10 to the power minus 4 centimeter. So this will be our least count. So I hope in this topic you will achieve something and try to figure it out where you have doubts, and try to solve more and more questions in this topic. I hope you are doing your best and to find out your dream college in the very next year. I think we should leave now. This is with this we complete our topic, that is error.